So for today's lecture, we will start with the applications of definite integral. Okay, we'll do one application today, and in the next few meetings, we will have some more applications of the definite integral. So for today, we'll be considering some regions which is enclosed by the graphs of some functions, and then we will try to find the area of the regions. Okay, so this is the area problem. Let f and g be continuous on the closed interval AB such that f of x is greater than or equal to g of x for all x between for all x in the interval AB. And let R be the region bounded by the graphs of y equals f of x and y equals g of x, and the vertical lines x equals a and x equals b. Okay, so for example, in here, this guy here, okay, so this guy here is your function g of x, and this guy here is your function f of x. And as you can see, when we say that the function, okay, f of x is greater than or equal to g of x, the graph of the function f of x is above the graph of the function g of x. Okay, and of course, this is your x equals a, and this is the x equals b. And the region we are interested in is this guy in here. Okay, so our goal is to find the area of this region. And to do this, the methods that we'll be using have been discussed so many times in the previous, so you should be familiar with this method. So first step is we divide the interval AB into n subintervals, and in this case we divide it into n subintervals of equal length so that we can have your delta x to be equal to b minus a over n. And such that let us name the endpoints of these subintervals. Okay, we start with x sub 0, which is equal to a, and that is less than x sub 1, less than x sub 2, etc. until we have less than x sub n. And our x sub n, that's b. Okay, that will be the b here. Now for each subinterval, x sub I minus 1, comma x sub I, we choose a sample point x sub I star. So in here, we have this case, or this point here, which is this guy here. Okay, and then we consider the ith vertical rectangle, and the height of this ith vertical rectangle, it is equal to the evaluation of the function f at x sub I star minus the evaluation of the function g of x at x sub I star. So in here, this is the point um, x sub I star, comma g of x sub I star. And then here we have the point x sub I star, comma f of x sub I star. So we evaluate the functions at x sub I star, and we have this and this point, and then we consider this rectangle here. Okay, and the height, it's the difference f of x sub I star minus g of x sub I star. And of course, the width of this rectangle, which is just this guy here, it's equal to the delta x. Okay? And then, of course, we form the Riemann sum. Okay? We form the Riemann sum of f of x sub I star minus g of x sub I star times g of x. We add all of them. Okay? We add all of them. So the area of this rectangle plus the area of this rectangle plus the area of this rectangle, etc. until you have this part here. So the sum will approximate the area of the region R. Okay, and to remove all those discrepancies, okay, the excess and those spaces in here, we will let n go to infinity. Okay, and letting n go to infinity, we will now have the actual area of the region R. Okay, and if the limit exists, okay, if this limit exists, then this is equal to the definite integral of f of x minus g of x dx from a up to b. Okay, so the methods, it's the same as the one we did before, and I hope you've memorized that one. Okay, now what if we have a different situation? Suppose instead of y equals f of x, y equals g of x, we have x equals f of y and x equals g of y. So technically, these guys here may not be a function. Okay, they might not be a function. But anyway, suppose we are forced to write the expression as x in terms of y, just like this guy here and this guy here. So this guy here and this guy here. Okay, so suppose these two guys here, okay, as a function, as functions of y, okay, they are continuous on the interval CD. Okay, so how is that? In here, this is your C, this is the C, and this is the D. Let's say this is, I think this will be the D. Okay, the D here. So the interval will be, okay, will be along this y-axis. And suppose that our f of x, our f of y is greater than or equal to g of y. Okay, for all y inside the interval CD. So in here, this guy here, okay, it means that the function f of y, okay, the function f of y is always to the right of the function g of y. So in this case here in the drawing, this is your x equals f of y, whereas this guy here, this is your x equals g of y. So as you can see, okay, in this illustration, the function here, f, it's always on the right of your g of y. Okay, so the function x equals f of y, it's always on the right of this function x equals g of y. Okay, and to find the area of the region A, okay, to find the area of the region A here, say this is your region R, sorry, to find the area of the region R. So this is your region R, and we are interested on finding what is the area of the region R. We will do the same thing, okay? The same thing. So the same method, we will divide the interval CD, okay? We will divide the interval CD into n subintervals of equal length. So this time, the division or subdivision will be somewhere here. Okay. Okay. And then we do the same naming, but this time in terms of x, instead of x sub 0, x sub 1, etc., we will have y sub 0, y sub 1, etc. Okay. So in here, we will have some delta y. This is d minus c over n. And then we have c, this is equal to y sub 0, less than y sub 1, less than y sub 2, etc. until less than y sub n, and y sub n, this is equal to d. Okay? And then on the ith subinterval, say this is the ith subinterval in here, we will choose some y sub I star. Okay? So say this guy here. So this point here, this is y sub I star. Okay? So the interval in here, this is the ith subinterval. Interval. And that ith subinterval, of course, it's just y sub I minus 1 comma y sub I. Okay? Then on this ith subinterval, we choose some y sub I star, which is here. And then we will evaluate the two functions, f and g, at this y sub I star. So at some point, we will have somewhere here and then somewhere here. And we will be able to create or construct a rectangle. And the length of this rectangle here, okay, the length of this rectangle here, it will be f of y sub I star minus g of y sub I star. Okay? So that will be the length of the rectangle. And then the width here, it's your delta y. So if we get all those rectangles, okay, if we get all those rectangles, we will have the area of each rectangle will be f of y sub I star minus g of y sub I star times delta y. Then we get the Riemann sum, okay? And we get the limit as n approaches infinity. And we will end up with the definite integral of f of y minus g of y dy from C to D. Okay? So it's the same. Okay? And as you can see in this illustration, the approximating rectangle is horizontal. Okay? On the other hand, in the previews, the approximating rectangles here are vertical. Okay? Questions so far? So those will be some of the hints that you would get, okay, or you will be provided in order to write the definite integrals. Okay, so in order to calculate the area, here are some suggested steps. Okay, here are some suggested steps. So in order to find the area using definite integrals, okay, these are some suggested steps. First, you sketch a graph. Okay, sketch a graph for each given function. Okay, just like in the illustration from before. Okay, there are some sketches because you will easily visualize which one is bigger or which one is smaller or which one is to the right or to the left. Okay, or which one is above or below. Okay, now you write all functions as y equals something in terms of x. So you isolate y, okay, on one side of the equation and the other side will be in terms of x. That's one way. Okay, and then if you have this case, okay, you use vertical strips or vertical rectangles. Okay? And the variable of integration will be in terms of x. Okay? So for example, in here, you have the function here y equals g of x, and then y equals f of x. So the functions are written as y in terms of x. So y equals g of x, y equals f of x. So y in terms of f of x. And the rectangles or the approximating rectangles, it's vertical. And then we did this, and the variable of integration is x. Okay? The variable of integration is x. Okay? Another possibility, you can write all the functions as x in terms of y. Okay? So you isolate x on one side of the equation, and then you write everything on the right side. That will include the constants and the y's, etc. And in this case, your approximating rectangles are horizontal. So you use horizontal strips, and the variable of integration is y. Okay? Just like what we have in here. So we have this horizontal strip here, okay? And then the variable of integration is y. Okay? Next. Okay? If if we have an integral with respect to x, okay? Always remember this: above function minus below function. Okay? So above function minus below function. And if, okay, if we have the variable of integration with respect to y, remember right function minus left function. Okay? Let us go back to this guy here. F of x is above function, g of x is below function. So above function minus below function. F of x minus g of x. In here, your f of y, it's this guy here, okay? And then your g of y, it's this guy here. So you have here right function, that's your f of y, minus the left function. That's your g of y. Okay? So if in terms of x, above function minus below function. In terms of y, right function minus left function. Okay? I will tell you the importance of those phrases. Okay? Later in the example. Now, if the function intersects, always find the points of intersection. Okay? Why? Um, these points of intersection will give you the interval. Okay? It will give you the interval for which you will integrate the above function minus below function, or right function minus left function. So always find these points of intersection. Okay? And like I said, you have to know this: above function minus below function, or right function minus left function, because it is possible that at some point or at some interval, your function f is greater than the function g. And on another interval, they will interchange location. The function g becomes greater than the function f. Okay? That's why I always ask my student, or I recommend my students to remember this. instead of f of y minus minus g of y, or f of x minus g of x, because there are some possibilities that they will cross over. Okay? Questions so far? Okay, so let's try this um, new topic or new concepts that we learned, especially these suggested steps. Find the area of the region bounded by the graphs of y equals ln of x, y equals 0, that's your x-axis, x equals 1, and x equals 2. So let's start with the sketch of the graph of these functions here. So this is your your y-axis and your x-axis. So this is your x, this is your y. Just try to sketch, okay? And then your ln function will be something like this, okay? So this is your y equals ln of x. And this point here, this is just 1, okay? So we have this ln function here. And then we have y equals 0. That's just the x-axis. So it's already drawn in here. It's this guy in here. Okay? Then x equals 1, we have this. You can draw that vertical line if you want, but you will see that you won't actually need that vertical line. And then maybe this is where your 2 is. So this is 2. So you have x equals 2. Okay? So the region, okay, the region is bounded by all of these functions here. Okay? Or the all of these equations here. Y equals ln of x, y equals 0, and the lines x equals 1 and x equals 2. So the region must be inside all of these guys here, which means that the region we are interested in is this guy in here. Okay? Which means that our interval will be from 1 up to 2. Okay? And then, if you look at this, the above function, it's your y equals ln of x. And then the below function, that's your y equals 0. Take note that this guy here, it's still written as y equals something in terms of x. It's just that it's equal to 0, so you don't see the x. Okay? Therefore, we have identified our region. Okay? We have identified our region. The area will be equal to the integral from 1 up to 2 of the above function, that's your ln of x. As you can see, ln of x is always above the y equals 0 on the interval 1 to 2. So you have ln of x minus the below function, which is y equals 0. For emphasis, I'll put this 0 here. Okay? I'll put that 0 there. And then you have your dx. Okay? So in here, well, we have this in terms of x. So it was not said in here, but your approximating rectangles are vertical. Okay? Your approximating rectangles are vertical. Okay? So anyway, let us solve this integral here. And You can do your integration by parts, okay? Or you can just write immediately the integral of ln of x dx. So if we do that, we'll just have x ln of x minus x. And then we evaluate this from 1 up to 2. So this is equal to 2 ln of 2 minus 2 quantity minus 1 ln of 1 minus 1. So if we simplify this, this is simply 2 ln of 2 minus 1. So that's the area of this region. Okay? Okay. Let's have another example. Find the area of the region bounded by the graphs of y equals x squared and y equals 2x minus x squared. Okay? So let's start with the graph again. Okay, let's start with the graph again. Suppose we have this. So this is your x, this is your y. We have y equals x squared. So y equals x squared, it's something like this. Okay. Okay. So this is your y equals x squared. And for this guy here, y equals 2x minus x squared, um, let's just try to find a way on how to sketch this guy. So you have y equals, or let me use another ink here. You have y equals 2x minus x squared. You can rewrite this as 1 minus 1 plus 2x minus x squared. Agree? And then we can even rewrite this as 1 minus quantity x minus 1 quantity squared. Okay? Very good. And notice that you now have y equals 1 minus x minus 1 quantity squared. This is just a parabola. Okay, this is just a parabola. And the graph will be, so here, this is a parabola. Parabola opens downwards. Okay, vertex. The vertex will be at 1, comma 1. Okay, so I hope you recall this object here. But anyway, so say this is your x equals 1. Okay, of course maybe y equals 1 in here, and then you have the vertex in here. Okay, and then if you sketch this, you will have the parabola that looks something like this. Okay, so this guy is your y equals 2x minus x squared. Okay, so where is the region? The region must be enclosed by these two functions. the region will be this guy here. Okay? Now, when I draw or when I drew this graph here, okay, the graph of y equals 2x minus x squared, I told you that they will intersect at this point. And somehow I also give you the hint that they will also intersect at this point here. But you have to calculate them. You have to calculate the points of intersection to verify that those are indeed the points of intersection and they will not intersect at any other points. So in here, points of intersection, all you need to do is to equate them and then solve for x. You have x squared. This is equal to 2x minus x squared. Or you can rewrite this as 2x squared minus 2x equals 0. You bring these two guys here to this side of the equation. So from the right-hand side, you bring them to the left-hand side, and you will end up with this. And from here, you can just factor 2x, and you will have, inside the parentheses, x minus 1. And that's equal to 0. So this means that you have x equals 0 or x minus 1 equals 0. Or in this guy here, we have x equals 1. And indeed, this is your x equals 1. This is your x equals 0. And therefore, your interval will be from this point, which is your origin, up to this point. Okay? Now, your functions, they are written as y equals x squared. And the other one is y equals 2x minus x squared. So y in terms of x, and according to the hint that I gave you in the suggested steps, when your functions are written as y in terms of x, the variable of integration will be x, and the approximating rectangles will be vertical. Okay? They will be vertical. So in here, let's just draw this vertical strip. And this vertical strip here, okay, and this vertical strip here will move going up there and going down here. Okay, but as it moves from down here going up there, the value of x actually moves. Okay, the value of x here actually moves on this interval from 0 to 1. So indeed, your interval is from 0 to 1. Okay? So, the area of the region will be the integral from 0 to 1. And here, on the interval 0 to 1, all throughout, the function above is y equals 2x minus x squared. So, y equals 2x minus x squared. That's the function above. And then the function below, it's your y equals x squared. All throughout the interval, 0 to 1. Okay? So, minus x squared. And now you have your dx in here. So, above minus below. above function minus below function. Okay? Questions so far? Now listen. This guy here, okay, this guy here, we call this the setup. So this is the setup in order to find the area of the region. Okay? There will be times where I will only ask for the setup. If I only ask for the setup, you will only write up to this point. Okay? For example, set up the definite integral that will give the area. So it's just this guy. You don't have to solve that because I'm just asking for the setup. Okay? In the future, I'll be asking, set up the definite integral that will give the volume, blah, blah, blah. So you'll just write up to this part. Similar, well, when we discuss the formula for the volume, you will only write up to this point. Okay? So we call that the setup. All right? But of course, for now, in our discussion, we'll calculate this. We will calculate this. So we have the definite integral from 0 to 1 of 2x minus 2x squared dx. So in here, we will have x squared minus 2x cubed over 3 evaluated from 0 to 1. And this is just 1 minus 2/3. Of course, we have at x equals 0, it's just minus 0. So this will just be 1/3. So this is the area. The area of this is equal to 1/3. Okay, understood. Let's look at our next example. Find the area of the region bounded by the graphs of y equals sine x, y equals cosine x equals 0, and x equals pi over 2. Okay? So let us look at the graphs. Let's try to sketch the graphs of these functions here. So this is your x, this is your y, and suppose this is your 1 of the y. And suppose this is your pi over 2. This is the pi over 2. So what is the graph of the cosine function? For the cosine function, we will have something like this. Of course, it will be 0 there, etc. I don't care about the graph beyond x equals pi over 2. I'm only starting at x equals 0 here. So I just started at this point here. But you can continue if you want. But we don't need that. Okay. And then the graph of your sine function will be something like this. So in here we have something like this. Okay? It's not accurate. It's not accurate. The graph is not accurate, but of course, after this, it will go down there, etc. But we don't need that part. Why? Because the other boundaries will be x equals 0 which is this guy in here, and then x equals pi over 2, which is this guy in here. Okay? So the region must be bounded by at least 3 of these guys between the sine function and the cosine function, and between x equals 0 and x equals pi over 2. So the regions are this guy here. Let us look at this. So this region here and this region here. So you have two regions. And if you look at only at the graph, you have some point of intersection at this particular point. Okay? And as you can see, from this x equals 0 at to this point, whatever that one is, okay, the above function is this cosine function, and the below function is this sine function. So that's from this interval. And then on the other side, on the other interval here, the above function is your sine function, and then the below function is your cosine. So they interchange location. So you need to determine what the point of intersection is. And some of your classmates already gave me the point of intersection. It's equal to pi over 4. So let's compute. Let's compute that pi over 4. So in here, points of intersection. In fact, there's only one point of intersection at this on this interval, 0 to pi over 2. So let me remove this s here. But yeah, we want cosine x equals sine x. Okay? Or this guy here, you can rewrite as sine x over cosine x, and this is equal to 1. And in here, let us specify. We are only on the interval 0 to pi over 2, and I'll put open interval. Okay? So we can divide by cosine. Because if we include pi over 2 in here, cosine pi over 2, it's 0. So we cannot do this division. Okay? And then from this quotient, you just have tangent x equals 1. And then from here, you will have what? X equals arctan of 1, and this is equal to pi over 4. So indeed, your classmates are correct. So thank you for giving that point, which means it's not really accurate in this drawing, but yeah, this is your pi over 4, and therefore the area of the region will be divided into two parts, this region here plus this region here. So for the first one, we have the integral from 0 to pi over 4. The above function, it's your cosine function here. Cosine x minus the below function, it's your sine function here. Dx. Then plus integral, this time from pi over 4 up to pi over 2. And in here, the above function is now the cosine function, and the below function is your, the above function is your sine function. The below function is your cosine function. So this time we have sine x minus cosine x dx. Okay? So if I ask you to set up only the definite integral, you'll stop your answer at this point, just the setup. Okay? But for us, for this discussion, we'll calculate the actual area. So in here, integral of cosine x, that's just sine x. Integral of sine x, that's negative cosine. So we will have plus cosine x here. And then we evaluate this from 0 to pi over 4. Then plus. Here we have the integral of sine, that's negative cosine x. And then here, integral of cosine, that's sine, but we have minus there, so we have this. Then we evaluate this at pi over 4 and at pi over 2. So calculating, for the first part here, at pi over 4, you have square root of 2 over 2 plus square root of 2 over 2. Correct? That's the value of cosine pi over 4 and sine pi over 4. Then minus sine 0, that's just 0, plus cosine 0, that's 1. So that's the left here. For this guy here, we have cosine pi over 2, that's 0. So we have 0 here. And then sine pi over 2, that's 1. So we have minus 1 in here. Then minus quantity. At pi over 4 again, we just have this square root of 2 over 2. So we have minus square root of 2 over 2 minus square root of 2 over 2. So what will happen here, if we simplify, this is square root of 2 over 2 times 2. In fact, that's times 4, because here minus minus and we have minus in here. So they become plus. So we have 2 square root of 2. And then here you have minus 1. And then there's a minus 1 also here. So you have minus 2. So this is the area of the region. Okay. Questions? So again, like I mentioned earlier, there's a possibility that the locations of your function, okay, functions will change. On one interval, function f is greater than function g, and then on another interval, the function f is less than the function g. So you have to remember that above function minus below function, or that right function minus left function if we have functions x in terms of y. Okay. Another example here. So find the area of the region bounded by the graphs of y equals x minus 1 and y squared equals 2x plus 6. Okay? So look at this. Here we have written y in terms of x. It's just a linear function in here. But here, notice that the variable y is squared. So if we try to get the square root of this guy just to write y in terms of x, we will have two values, the plus part and the minus part. Okay? So instead of doing that, if we look at this, we can easily isolate x. So we can write x in terms of y. So if that's the only way to do that here, so that we will have easier analysis, we will do the same thing in here. We will write x in terms of y. Okay? So for this guy here, we will have 2x equals y squared minus 6, or we have x equals 1 half y squared. Let me write that 1 half y squared minus 6 over 2, that's just 3. Okay? And then for this guy here, we will have x equals y plus 1. Okay? Then let's sketch. Let's sketch the graphs of these two equations here. So for this guy here, let's just get 2 points because this is just a line. So if we have 2 points, then we will be able to determine the unique line. So for example, when x equals 0, y equals -1. So suppose -1, it's here, +1, it's in here. So when x equals 0, y equals -1. And then when y equals 0, x equals +1. So if this is your x in here, we have this. So we'll just have the line. Okay? So we have this line here. So x equals y plus 1. And then for this, we have a parabola. Okay, we have a parabola which opens upwards, and the vertex will be, sorry, we have a parabola that opens to the right. Take note of this, we have x and then the squared part, it's y. So it opens to the left or to the right. Okay. When y equals 0, x equals -3. So 1, oops, we have here 1, 2, and then 3. So this is -3. Okay. And then what? When, let's say, y equals 2, or y equals plus or minus 2, let's just try to estimate. This is +2. Then if we go down here, we have here -2. So you have x equals 1 half y squared minus 6 or minus 3. When y equals plus or minus 2, we have x equals 1 half times 4 minus 3. This is equal to -1. So x will be equal to -1. So let me extend this part here. So in here, we have something like this. Okay. And then we have something like this here. Okay. So if we try to extend this, let us just extend this part here. Anyway, the graph of the parabola will be something like this. Okay. At some point, there will be some intersection here and in here. So we need to identify the points of intersection. Okay? And since we have written x in terms of y for both of them, the variable of integration will be in terms of y, and the approximating rectangles will be horizontal. So the approximating rectangles will be horizontal. Okay? So if you move this rectangle going up there, going down there, so you will have this approximating rectangle somewhere here. You will have the approximating rectangle somewhere here. And then the approximating rectangle somewhere here. All throughout, all throughout the movement of your approximating rectangles, the right function is given by this line. The left function is given by this parabola. Okay? So the right function is given by this line. The left function is given by this parabola. So right function minus left function. But again, we need to identify the interval of integration. And you will be able to identify that when you found these points of intersection here and here. Okay? Because, well, if you try to move this approximating rectangle, it seems that the highest point will be at this point of intersection here. The highest point will be there, and the lowest point will be somewhere here. Okay? So we need to find the points of intersection. So let us calculate points of intersection. Again, you just equate. You have this time y plus 1 equals 1 half y squared minus 3. Okay? So there was a question here. Why did we do this y equals plus and minus 2? I just used them. Okay, I just used these two guys to approximate the sketch of the graph. I know that this is a parabola. Okay, I know that this is a parabola because of the given equation. I just need another 2 points. I know this will be the vertex. So I will need other points so that I can approximate at least the sketch of the parabola. You can use other points if you want. You can use other y's. Okay? All right. So anyway, let us solve. Let us solve for y in here. We will have 2y plus 2 equals y squared minus 6. Or we rewrite this as y squared minus 2y minus 8 equals 0. You can use your quadratic formula to solve this. I'll just use factoring. This is factored into y minus 4, y plus 2, which means that I have here y minus 4 equals 0. The other guy, it's y plus 2 equals 0. So you compute, you have y equals 4 and y equals negative 2. Indeed, my value here is accurate. They intersected at y equals negative 2. Okay? And then in here, this guy here has y coordinate equals 4. So it must be somewhere up here. Okay? The scaling here, it's not precise. In fact, the graph, it's not really accurate. Let me adjust that. Let me just adjust the graph. Okay? So the graph of this parabola, it's still way up there. Okay? So it's still way up there, maybe. Let's have that. Okay, so the point will be somewhere here. Just an approximate location. Okay, but yeah. Okay, etc. in here. So anyway, the point is, you know that the highest value for y will be somewhere here. It's y equals 4. The x, well, it's just 5. X equals 5, y equals 4. But we don't care about the x values. The point of intersection down here, it's -1 comma -2. But again, we don't care about the x value. We just need the y value because that gives us, or those give us the endpoints of the interval for our integration. So the area will be integral from -2 up to 4 of, again, right function. It's your y, it's your x equals y plus 1. So you have here y plus 1 minus the left function, it's your parabola here. So minus quantity 1/2 y squared minus 3. And then you have the y. Okay? So again, this is the setup, but we will finish the solution here. Let us calculate for the actual area. We have here y squared over 2 plus y minus, we have here y cubed over 6. And then here you have minus -3y, so it becomes plus. Sorry, minus -3, so it becomes plus here. And then if we integrate that, we'll just get 3y there. And then we evaluate this from -2 up to 4. So let's just calculate the integrals here, or yeah, let us evaluate this guy here from -2 to +4. So you will have 16 over 2 plus 4 minus 4 cubed. That's 4 times 16. 16 times 4, that's 64. So 64 over 6 plus 3 times 4, that's 12. Then minus quantity, -2 squared, that's 4 over 2. Then y equals -2, so minus 2. Then here minus -2 cubed, that's -8 over 6. Then plus 3 times -2, so we'll get minus 6. And then all we need to do now is to simplify this. Okay? So in here we will have 8 plus 4, that's 12. plus 12 in here, that's 24. And then in here, 4 over 2, that's 2 minus 2, so this will cancel each other. And we have the minus 6 here, but we have minus here, so it is again plus. So 8 plus 4, that's 12, plus 12, that's 24, plus 6, that's 30. And then we have minus 64 over 6, minus 8 over 6. So minus 64 minus 8, that's 72. And then minus 72 over 6, that's what? 12. So we have minus 12. So this guy here, this is equal to 18. So the area is 18 units squared. Okay, so please check my arithmetic there. If my arithmetic is correct, then we will have this as the area. Other questions? Let's have another example here. Find the area of the region bounded by the graphs of x equals 1 minus y squared and x equals y squared minus 1. So the graphs or the functions here, it's x in terms of y. Okay, well, technically they are not functions. Okay, but if we look at y as the independent variable and x as the dependent variable, then you have you also change the orientation of your function. Okay. Okay. So let's do this first. Let us start with the sketch of the graph. So this is your x, this is your y. For this guy here, you have x equals 1 minus y squared. Okay, so x equals 1 minus y squared. So this is a parabola which opens to the left, and vertex will be 1, comma 0. So say this is 1, this is the 1 for y, negative 1 for y, negative 1 for x. So for this, we have the parabola that will look something like this. Okay, so this guy here, it's your x equals 1 minus y squared. And then for this guy here, x equals y squared minus 1, this is a parabola that opens to the right. And the vertex will be negative 1, comma 0. So we have the vertex in here. The parabola will be something like this. Okay, so this purple here will be x equals y squared minus 1. So you expect the region, it's just this guy here. Okay? So, for this, let us start with the points of intersection. As you can see, they will intersect, well, I graphed it almost correctly. They will intersect at this point and at this point. But let us calculate that one. So to calculate that, you just need to equate them again and solve for the value of y. So points of intersection, we have 1 minus y squared equals y squared minus 1. So this is just what? You will have 2y squared minus 2 equals 0. So you bring this side here to the other side of the equation. So from the left-hand side, you bring them to the right-hand side and you will end up with this. Then you can factor 2 and you will have 2 times y squared minus 1 equals 0. And y squared minus 1, it's factorable into y minus 1 times y plus 1. Which means that we have y minus 1 equals 0 or y plus 1 equals 0. Or we got y equals 1, y equals negative 1. So those are those 2 points. The y values are negative 1 and positive 1. Okay? So the x coordinates, they are just 0. So 0, comma 1, 0, comma negative 1. By the way, points of intersection, I did not write it in the previous examples. Points must be written in this form. Okay? So these are the points of intersection. Okay? It's not just y equals 1 or y equals negative 1. The points is an ordered pair, x comma y. Next, in here, we have written x in terms of y, x in terms of y. Both of them. So we can easily deduce that we can use y as the variable of integration. And therefore, we are going to use horizontal strips. So if we do horizontal strips, we'll have this guy here. You move this going up there or going down here. Okay. The highest point will be at this point. That's your y equals 1. The lowest point will be at this point. That's y equals negative 1. So the interval will be from negative 1 to positive 1. Furthermore, the right function is this parabola here. Okay? So the right function is this parabola here. The left function is this purple parabola here. And that's all throughout the interval from negative 1 up to positive 1 in here. Therefore, area will be the integral from negative 1 up to positive 1 of right function, it's 1 minus y squared, minus the left function, it's y squared minus 1. And then we have the dy. Okay? And then from here, I'll now ask you to do this. So continue. All you need to do is to integrate this, and therefore you will get the area. Okay? Questions? Last example for this session. find the area of the region bounded by the graphs of y equals, sorry, this should be x to the 4. Okay, this should be x to the 4. So let me change that. So y equals x to the 4 and y equals 2 minus absolute value of x. Okay. So for this, again, we sketch your y equals x to the 4. The graph will look like the graph of y equals x squared. Okay. So it will look something like this. Okay. So this is your y equals x to the 4. And for the y equals 2 minus absolute value of x. So you know the absolute value of x, it's v. Okay. It's just your v. But we have a negative here, so we have an inverted v. And then we shift it 2 units upward. So say this is 1 here, 2 here. Okay. The absolute value, this guy here, y equals 2 minus absolute value of x, will be something like this. Okay. And of course, x equals, if x equals plus or minus 2, it will intersect at this part here and at this part here. But anyway, what you need is the intersection here and in here, because the region is at this, is inside here. Okay, this is the region. But I'll give you a hint. This guy here, the x coordinate, it's -1. This guy here, the x coordinate, it's +1. Okay. And then, since you have y in terms of x, also here, y in terms of x, we'll use vertical strips. So say this is that vertical strip here. This vertical strip will move from left to right. So from left to right. And all throughout, the above function is this y equals 2 minus absolute value of x. The below function, it's your y equals x to the 4. Okay? Questions so far? So now I have given you the situation, this sketch here. So I want you to set up the integral. In fact, give me the area of the region. Okay? Give me the area of the region for this situation. Okay?